Today, I'm pleased to introduce today's session, Vector Search Best Practices, and our guest speaker, Yujin Tang. Yujin is a developer advocate here at Zillis. He has a background as a software engineer working on AutoML at Amazon. Yujin studied computer science, statistics, neuroscience, and research papers, with research papers published to conferences including IEEE Big Data. He enjoys drinking bubble tea, spending time with his family, and being near water. Thank you so much for joining us. Welcome, Yujin.
Thanks for the thanks for the introduction, Emily. Thanks for everybody for joining. Today, I'm going to be talking to you guys about vector search best practices. We're going to learn about vector embeddings, what they are, how to use them, when to use them, what to do with them, and how you can use a vector database. So a little bit about me. My name is Yujin Tang. I put a QR code on here. If you happen to have your phone handy, you can scan this QR code and you can find me on LinkedIn, which is where I'm the most active. If you aren't on LinkedIn, you can connect with me via email or via Twitter. So yeah, and as Emily was saying, my background is in software engineering. I've been at Amazon, I've been at IBM, and I've worked on many ML systems. A little bit about Zillis. You can find us on Twitter at Zillis Universe, on LinkedIn at Zillis. You can also go to Slack. You can go to Milvus.io, Milvus.io/Slack, or you can find Milvus, the open source vector database, on GitHub. So a little bit of point here, Zillis is the company, Milvus is the open source vector database that is maintained by Zillis. Okay, so let's get into it. What are we going to be covering today? We're going to be covering these basic 4 topics here. Why do I need a vector embedding? What's a vector embedding? How do vector databases work? And how you can get started with a vector database. Okay, so let's get started with this one. Why do I need vector embeddings? Unstructured data is everywhere. This is something that I'm sure many of us have heard many times now, is that 80% of data is unstructured data, and that 90% of that is never analyzed. As we go into this more machine learning, AI forward industry, universe, whatever world that we're moving into with these LLMs dominating the scene now, where there's going to be more and more unstructured data, and that structured data is going to start getting analyzed. And this is kind of how, or this is why you would need a vector embedding, because vectors can be used to represent this unstructured data that doesn't fit a predefined data model. So you can use it to represent text, images, video, audio, molecules, many different things. So this is part of why vector embeddings are so important. So where can vector databases help? What can vector databases actually help with? These are some of the topics that vector databases are used in a lot. Many of these are more conventional topics, such as image similarity search, video similarity search, audio similarity search, so on, text similarity search, and so on. And later on, I'm going to be showing some code on how to do some image similarity search and how to do some text similarity search. We won't necessarily get into all of the details, but I'll show you some code to kind of understand and get started. And then the link to the notebooks will be dropped either in the chat or afterwards. Oops. Okay, so these are some of the more interesting or larger use cases for vector databases that I'm going to go into that I've kind of seen around. So number one is adding data to LLMs. So for example, LLMs right now are not trained on completely up-to-date data, and they're not trained on your internal private data. So if you want to use an LLM in production at an enterprise scale, you're going to want to add some data to it. And these are some examples of tools that you can use in this space. So GPT Cache, for example, this is a caching tool for GPT that we made. It's open source, it's got almost 5,000 GitHub stars, pretty popular. Then there's Llama Index, which if you've heard of, is a data framework, is a framework for accessing your data with LLMs. And I built quite a few things with this, and I'm sure that some of those links will also be available. And then there's OSS Chat, which you can go and check out at osschat.io. This is basically, it allows you to chat with open source software. And what this is an example of an app that adds data to LLMs following something we call the CVP stack. And I'll touch a little bit more on that later. But basically, this demonstrates how a vector database can be used to add your internal data or your personal specific data. So in this case, that data would be the open source software documentation. and how you can add that data and query that data and essentially chat with that data using a chatbot and a vector database. Other things vector databases can be used for include things like product recommendations. This is very, very common. This is very popular. And one of the reasons for this is actually, and I'll probably touch more on this later as well. You don't need you don't need like super high accuracy for product recommendation because you're going to find the product that you want. You just need to be able to find it within a couple clicks. So this is an interesting use case where there's many, many different ways to do this, but vector databases are particularly good at finding the most similar products. Then there's reverse image search, which is basically reverse image search. This would be similar to kind of the product recommendation kind of category. Let's say you have a picture of something and you want to find something similar to it. So I've created a mini fashion AI project that basically does this with like articles of clothing. But in this example here, you see it, it's food. It returns the closest images to some food based on the images that you give it. The most, I guess, the thing that has made vector databases much more popular recently is this generative AI, right? These LLMs. And so that kind of falls into this text search engine, this text Q&A kind of bot, question answering kind of thing. That's kind of where this falls in. And so we're going to zoom in on this and we're going to take an example use case and just kind of understand how you or an enterprise could use a vector database to create a generative AI app. So for example, you have hundreds of thousands of pages, maybe millions of pages of proprietary internal documentation so that your staff, your customers, these people who need this information can go and get what they want done. So if your customers come and they ask you a question, most of the time you're going to need some sort of customer service rep to do this. But you can also automate a lot of the easy questions, the ones that can be answered almost automatically through using a vector database and an LLM. And it'll be faster because searching through these millions, hundreds of thousands of pages requires some sort of internal expertise from the customer service rep or whoever is doing the searching. And so instead of having someone waste that much time doing that, what you can do is you can use these LLMs to understand the customer query or the user query and then put that into the vector database and use the LLM to find the correct, most similar documentation. Okay, so what is a vector embedding? I've talked a lot about vector databases, how you can use them, why you need them, right? There's a lot of unstructured data. There's a lot of data that needs to be represented somehow, and vector embeddings are basically the answer to that. So let's get an introduction to vector embeddings. I love this image. This is an image from a very seminal paper from Suter et al. And this is about vector embeddings. What is a vector embedding? Why are they important, right? So basically what vectors allow you to do is they allow you to access knowledge that you don't have a structure for, right? And so in this example, what we see is we see the words queen, king, woman, and man. And what I want to show you with this example is that you can do math on words using vector embeddings, okay? And then ideally from there, we can extrapolate this. You can also do math on images, on audio, on, sentences, paragraphs, or whatever. But so for now, we start with this. We look at queen, look at king, and look at woman and look at man. So notice how queen and woman have the same first number, 0.3, and king and man have the same first number, 0.5. So now when you subtract woman from queen, you're going to end up with that first number is going to be a 0. That second number is going to be a 0.5. So if you add man to that, that first number is going to be a 0.1. That second number is now going to be a 0.7. Or the first number is going to be 0.5. The second number is going to be 0.7. And now you have the word king. And so basically what this image shows is that with these vector embeddings, you can do this math on words. Queen minus woman plus man equals king. And so this is a very, very simplified example. Traditionally, vectors are going to be in a much, much higher dimensional space. Right now, I'm showing you a 2-dimensional example. If you go and you use something like sentence transformers, you'll have 768 dimensions. And actually, we'll talk a little bit about that later on. So how are these vector embeddings generated? What determines how many dimensions they have? What determines what they are? So actually, what's really important for this is the model that you pick. A vector embedding is actually just the output of the second to last layer of the deep learning model that you decide to run. So in a traditional deep learning model, you have some sort of input, some sort of hidden layers, and then like an output layer. So this output layer is usually going to be some sort of prediction, some sort of classification. Maybe it's the location, maybe it's whether or not your place's location. Maybe it's predicting the next word, right? And like GPT's decoder architecture. Maybe it's finding the part of speech or something like that. This is a predictive kind of thing, right? So when you move one layer back, you have these layers, this layer of neurons, usually hundreds of neurons, and they provide some sort of output, and that output gets fed into the last layer. So that output is our vector embedding. So how can you make some vector embeddings, right? Is you're really going to, one of the most important things to choose when you are creating these vector embeddings is the model that you're going to use. You can spend hundreds of hours optimizing your indexing for perfect recall or perfect speed or whatever. Perfect isn't a real thing, but like for really good recall, really good speed, right? But it doesn't matter if your vector embeddings are wrong. So for example, these are some places where you can get vector embeddings. OpenAI has OpenAI's embeddings. These are 1536 dimensional. These are slightly bigger. Hugging Face allows, Hugging Face, there's just so many models on Hugging Face that you can use. And so Hugging Face is a hub for that. I think PyTorch also has some. I didn't put it on here. PyTorch also has some. And then there's ResNet 50. So ResNet 50 is available both on Hugging Face and PyTorch, and it's available in many formats. But this is an image architecture, and this is something that this is an image model, and this is something that you need to keep in mind as you create these vector embeddings. Is when I'm working with images, I have to use the image model to get my vector embedding. If I'm working with text, I have to use a text model to get my vector embedding. And actually, one thing that's come up a lot for from me like talking with people who are working with these is like using the right model for the right type of text. For example, if your text is a story or a novel, then sentence transformers, something that works on and is trained on complete sentences, would work really well for you. But if your text is in, let's say, CSV format, then sentence transformers may not be the best idea because it doesn't know what to do with these commas that are between all the words, or the /r/n kind of stuff, these characters, these special characters that go into CSV. Or PDF, right? So there's many formats that text comes in, and you have to think about that as you create these vector embeddings as well. Oops. Okay, so let's take a look at what vector embeddings look like. This is a question I get a lot because what does a vector database look like? What does it look like inside of a vector database? I say things about vector databases sometimes, and people are just like, okay, cool, this is like going over my head. I have no idea what you're talking about. Like, is this a key value store? Is this like just a bunch of numbers? Like, what's going on? So this is a screenshot straight up from Zillus Cloud. And this shows you what could be inside of a vector database. This is from our example data set. So our example data set is on Medium publications. And this one shows that, this is what one entry looks like. It shows the ID and the vector, right? So this is the important part to know, is that this vector is really just a long series of numbers. And then there's some other metadata here. So if you need metadata, Zillus Milvus also supports putting metadata into the database. Okay, how do vector databases work? Oh, I see there's a few things in the chat. Embeddings are specific to models. How would you search through embeddings of two different models? You have to search through two different embeddings. You have to search through two different vector databases, basically. Okay, so we're going to go over some vector indexing methods. So this will be talking about how you do the vector search stuff, right? So this is the vector search best practices part. So first thing we're going to look at is we're going to look at approximate nearest neighbors, oh yeah, or ANOI. This is a algorithm that came out of Spotify, and essentially what it does is it cuts your space, it cuts your space in half many times until you reach a certain predefined parameter, such as maybe the number of leaf nodes or the number of nodes in a leaf node. And what it does is every time it cuts your space in half, it creates a binary tree. it creates a binary tree by cutting your space in half multiple times. So the first thing you do is actually choose 2 random points. It does not matter what the points are. And then you classify them by finding the points that are closest to one and the other. And that's how you get your first half. And then you do that again within each half of those spaces. So that's Annoy. This is out of Spotify. This is a pretty decent index. It is not too space heavy because you're basically just saving the binary tree. And it's not too computationally heavy because you are only comparing to a few nodes once you traverse the tree. Inverted file index is the next one that we're going to cover. This is probably what I would say is the most intuitive vector indexing method. So if you have taken some intro to machine learning class, you probably know what k-means is, right? So k-means is a clustering algorithm that essentially says, here's some number of centroids. Find me the clusters by finding the points that are close to each centroid, and then that's going to be a cluster. And that's basically what IVF does. It says, okay, we're just going to find some number of centroids. We're going to group the points around them. And then when you come in, that's at indexing time. So at query time, when you come in and you search and you say, hey, I want to see, this vector here, what it does is actually it searches and finds the closest centroid, and then it goes into that centroid and it searches and it finds the closest point within the centroid. So once again, you can kind of see that the memory here is going to be pretty good, right? It's not you don't have to store too much memory for the indexing. And then you can also see that based on the way that you search it, you will most likely be getting the right results back as well. Then there's hierarchical navigable small worlds, or HNSW. This is a really, really, really popular vector indexing method. And one of the reasons why this is so popular is because it is extremely accurate. It is almost 100% guaranteed 100% recall. And the reason it works that way is because of the way that it works. So at index time, when you are inserting your data, it creates a graph. It creates a graph index of all of your nodes. So from that, you can kind of think like, okay, so we actually have to keep track of more information than just the nodes itself. So it's actually very memory expensive. But right now, one of the reasons why it's popular is because even though it's memory expensive, memory is not terribly expensive to buy right now. And people enjoy the accuracy. So how does HNSW work? At insertion time, every time you have a data set, every time you have a data point and you want to put it into your graph database, or sorry, your graph index, what happens is you assign it a uniform random variable. And based on that uniform random variable and how that compares to some sort of predefined parameter, it's going to go into a certain layer. So for example, if my predefined parameter is 0.9 and I'm inserting data points, if my data point, when I insert my data point, I generate a uniform random variable. If that uniform random variable is between 0 and 0.9, it goes into layer 0. If it's between 0.9 and 0.99, right, 90% of the next layer as well, then it goes into layer 0 and layer 1. If it's between 0.99 and 0.999, then it goes into layer 0, layer 1, and layer 2, and so on and so on and so on. So it's kind of probabilistic which layer a point is in, which is also interesting. This means that HNSW is actually non-deterministic when it creates the graph, unless you set the random seed. But at query time, what you do is you go into the topmost layer. So the number of layers that you'll get is also going to be probabilistic, by the way. But you go into the topmost layer, and then you say, what's the closest point in this layer? And you drop down and you say, what's the closest point in this layer? And you drop down, you do it again. So actually the only real calculations, the main real calculations that you have to do here are very short, because you already have this graph index built where you know where the closest nodes are to each node that is in the index. So yeah, this is a really accurate index, takes up a little bit more memory, but also fast query time. Okay, so how can you get started with a vector database? Okay. How can you get started with a vector database? So we're gonna cover a couple different use cases on vector databases and how they work. So let's first think about what is similarity search. Let's cover what similarity search actually is. This is what you are doing. This is what a vector database essentially handles for you. And this is the main reason why you would use a vector database, right? If you have things that you need to find how similar they are to each other, that's when you would go into a vector database. But if you have things like, key values, like for example, if you have a list of users, then you probably don't want a vector database, because with that, you want the exact response back. Because if I give you a username and it's only similar to another username, and you give me that password back, I'm not going to be able to verify my user, right? So vector databases are used for similarity search applications. And the way this works is you start with your unstructured data, step one, right? Some number of images, some number of videos, documents, audio, whatever, some sort of data, and you transform it into a vector. And this is the part that I was talking about earlier that's important is, right, you got to pick the right vector model when you are transforming your vector. Okay. And then once you transform it, you store it into your vector database. And then that's it. That's all you need to do for putting your data into a vector database, right? So from here, what you are concerned with is, how do I get my vector back? And essentially what you're doing is you're going to perform the query. And when you perform the query, you use the same model as you did before. You have to use the same model. That was a good question asked earlier, is like, what if you have two different models, right? You have to have two different vector embeddings for that. You have to have two different vector searches for that, two different collections or something like that. So once you get your embeddings from your query, then you run it into the vector database, and we do something kind of like this. Oh, I forgot to cover this slide. I'll cover this in a second. And then once you run one of these indexes, such as IVF or ANNOY or HNSW, then you get your results back, and you get to see where the most similar vectors are. Typically, you would ask for some number of results back, so maybe like a top 5 or like a top 3. Or something like that. Zillus Cloud automatically returns the top 100, so you can also go look at that if you would like. So this is a slide I skipped earlier, and I don't know how I skipped it, but this is important to understand. So why do you want a purpose-built vector database? What's the point of using a purpose-built vector database when I've just covered all of these indexes that you can just go use? You don't need a vector database to do these. You can implement them yourself. You can find them on some sort of open source repo or whatever. These are called vector search algorithms or vector search libraries, which provides you with some sort of high performance vector search instead of just brute forcing, right? So compared to these, what does a vector database have that makes it important? I think one of the most important things about having the vector database, at least with Milvus/Zillus, one of the really cool things is it allows this thing called dynamic schema, which you can basically insert new fields at insertion time, and you don't have to define it in your schema. And so this is really cool. This is great. This is what you can do with NoSQL, right? With SQL databases, you're going to have some issues if you play around with this table schema too much. But with NoSQL, you can kind of insert whatever you want, and we kind of have that dynamic schema ability. Number 2, I think, is like the filtering. So you can now filter on your metadata. Actually, I think you could do this before too, but you can filter on your metadata, which allows you to, say, perform more specific tasks. So let's say, for example, I want to create some sort of, I want to find the most common answers to a question that I get asked a lot, but I only want the answers that have come up in the last month. So maybe the question is something like, what's the most popular LLM? And I store all these answers in my vector database, and then I say, okay, well, I want to know in the last month what was the most popular LLM, right? So that is kind of one of the great things about filtering, is you can select on metadata. Or for example, with a Medium example, let's say I only want things from the publication UX Collective or the startup, right? I can filter these examples when I do my vector search. So naturally, one of the questions that comes up about the filtering, by the way, is do you filter the vectors before, or do you filter the vectors after? This is something that I get asked. And the actual answer is that you actually filter the vectors during the search. So this is also a really cool part of Milvus, is that this is an extremely effective and efficient search pattern, because what you do is you create a bit mask so that as you go through, you just mask your metadata with a bit mask, and it says whether or not you even want to consider doing these calculations. Are you recording? Where can I get the slides? Yes, we are recording. These will be sent out later. Other things that make a vector database important include, the very basic things, right? We manage the scaling horizontally, vertically, if you want a bigger CPU, bigger GPU. We also, this is specific to Milvus again, we have GPU support with NVIDIA, billion scale storage. If you want to, multiple nodes for your multiple instances, multiple servers for your vector database, we can also do that. Sharding for your streaming data, backups, lifecycle management, multi-tenancy, like role-based access control for enterprise users, really high TPS, transactions per second. These are the kinds of things that vector databases support, that a purpose-built vector database like Milvus supports. Do vector databases support ACID? Yes. Well, actually, so Milvus allows you a couple different types of consistency, but I'm pretty sure atomicity is pretty much always there. Consistency, there's what's it called? Eventual consistency, strong consistency, session consistency, and there's a fourth one. It is on the tip of my tongue. I do not remember what it's called, but basically they allow you different types of consistency. So yes, vector database. The short answer is yes, vector databases support ACID. So how do we implement this vector similarity search that I just showed you here? How do we implement this in practice, right? We're going to start with some sort of knowledge base, some images, some audio, some videos, some text, something like that. And we're going to run it through a deep learning model. And you have to pick the right model, right? You're going to have to pick the model that corresponds to your data. If you're using sentence data, use sentence transformers. If you're using CSV data, use something else. And then you're going to remember you have to cut off the last layer and you get the output, and that's the vectors. And you can put that into Milvus or Zillus or whatever. One more comment before I get into the code. I'm going to do the code really quickly so that we have some time at the end for some questions. I'm actually going to stop after this for some questions before I get into the code. But I will also, do the code quickly enough that we can get some questions in. This is a vector database benchmarking tool. Once again, the QR code is here. Scan the QR code. It's an open source repo on GitHub. If you download it, a lot of the benchmarking is already set. But you can also do your own benchmarking if you want to evaluate different vector databases, we do allow you to do that. Okay, so before I get into my code, I'm going to take some questions. And also this is another QR code that you can scan that will take you to the Milvus GitHub. Milvus is an open source vector database, right? And once you go there, you can download it, start it, check it out. Questions, okay. Oh, thank you, Chris. Yeah, so Christoph okay, cool, Emily, thank you for that. Is it true that vector search is linear boundary only? I actually don't know what linear boundary only means. What is that? I actually just don't know what that means. Vector search is like essentially you're taking some vector metrics like L2 or IP, inner product, right? Or cosine. Cosine is just normalized inner product, right? And you're comparing these using one of these you're comparing two vectors using one of these vector metrics, and you're just returning the closest ones based off of the metric that you chose. And you also have to ensure that when you insert, you choose the same metric as when you search, because that makes the most sense. If a model publishes a new version, will the dimensions change? Or if not, will they be compliant to the embeddings I already have in my database? Or do I need to recompute all embeddings and store them again? So this is actually, most times the dimensions won't change, but if it does, they'll put it into the model card. So for example, the sentence transformers model has had 768 for a long time, and it will probably continue to do that. OpenAI has 1536, and they will probably continue to do that as well. I think it's kind of uncommon for people to change the model architecture and call it the same model. Usually they would publish a paper that says, hey, we published this new model, because people want to have publications. And yeah, if not, will they still be compliant to the embeddings? Yes. Will you want to recompute them? Up to you. You can check your performance, see if it matters. is model training or parameter creation required before we can use the vector database? You don't have to train any models. You can go online, and online you can find models such as, through these resources, right? So you can go to Hugging Face, tons of models. You can go to OpenAI. You can use their OpenAI embeddings. Only works for text. You can use ResNet 50, which is also on Hugging Face, also on PyTorch, and this is for images. So you don't need to train, but you do need a model. You can train if you want a specific type of data. What do you think about the universal sentence encoding from Google for vector similarity? I think you can use it. I don't have any particular comments on it. Just that, yeah, I mean, it works, right? Okay, cool. It looks like we don't have any more questions on this presentation. So I'm gonna go ahead and slide over into the code. And then we're gonna take a look at this code. So we're gonna take a look at two pieces of code. There's tutorials that describe what these are doing available, but here I just wanted to cover these so that we can kind of take a look into picking a model, and also why that model is important, how this kind of changes over different types of text. So in this example, we are working on text data. And what we're doing here is we're gonna find we found some data set. It has this is where you can download it. This will all be available. So you can kind of replicate this yourself. But we have some data set. It is a set of White House speeches. And so the first thing we need to do is, as any good data scientist does, we read in our data set and we clean it up. So when you read it, you'll actually see that, I didn't start this server. Okay. So let's see if I can just start this server here. So when you start looking at the data, you can see that there's a lot of things to clean up, right? And then as you go and you clean up this data, so now you can see I've just done a bunch of things. I've dropped some NAs, I've checked for some speech lengths, whatever, and I've cleaned up the data. So now it looks nice. It looks like data that you could actually use. And you want to make sure that the data that you have, that you put in your vector database, is data that makes sense, right? Otherwise, it's not very helpful. This is actually not a very helpful code. Okay, so now we go from here. We can start putting things into the vector database. But actually what I want to show you is not that slide. That's not important. Where's the important one? Here we go. Okay. So what I've done here is I've used this thing to get sentence transformers, right? So sentence transformers, and this is a specific sentence transformer model that is all mini LM L6 V2. This is a model that is popular. And this is a version of the sentence transformer model. So this kind of goes towards what you were saying earlier, Christoph. If a model publishes a new version, most of the time the dimensions won't change. I think all of the sentence transformer models are at 768. As I show, oh, they're actually 384. Oh, I was wrong. Okay, they're actually 384. So this one's 384, but there are many that are 768. So I guess as they publish new ones, they will change. And then this is mainly what I wanted to show you about picking a model for your text data. And that's pretty much all there is to this one. I'm not going to run this much longer here. I don't think it needs to be. How can I? Okay, let me restart this one. And then the other one is paintings. So envision models, reverse image search, reverse painting search. Okay, so in this one, what we're doing is we're downloading some files once again. And this one's we're going to use PyTorch. So this one, last time we used sentence transformers, which is actually from Hugging Face. And this one we're going to use PyTorch, which is a different integration. So we have all these integrations, all these integration examples available on Zillow's Cloud as well. And in this one, we have a different dimension. As you can see, we have 2048, which is quite a few more dimensions. And basically, we start a vector database. It gets started. And then we create our field schema, blah, 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 put it in, put all the images in. And then here, this is where we pick the model, right? Is that we go into PyTorch, right? And then we load up some version of ResNet 50. And you'll see that I actually have this model cached here, but that's because I have already downloaded the model. So actually, if you need to download the model, you're going to have to do this SSL step first too, just to give yourself a context to be able to download this model. And it's important to know here, the couple important things I want to touch on here that you guys should see is, this gives you this like way to remove the second to last layer, to remove the last layer, right, using Python. And also that here we've defined the dimensionality up here. And that's because we knew ahead of time that this specific model has a dimensionality of 2048. If you don't know that ahead of time, then you probably need to either A, you can read the model card, or B, if there's not a lot of information on the model, you can run it through and then just check that yourself. And here, once again, we also, where is it? Where's the 384? Ah, here it is. Okay. So we also knew the dimensionality of the sentence transformers model before we set that up as well. And here we'll also note that you actually handle this kind of model differently than the PyTorch model. And that's because of the library itself, right? So PyTorch is a library that kind of allows you to build these neural networks, and it allows you to work on neural networks. So it kind of lets you cut these layers. Whereas transformers, or Hugging Face isn't really mainly focused on you building the neural networks, but rather using their models. So they actually allow you to just encode, this is just the function, the data, to get your vector embeddings. So that's mainly what I wanted to point out here. The difference between these text and these vision models are important to note, especially when it comes to dimensionality. And you cannot compare text data that is 384 dimensions to image data that is 2048 dimensions. Right now, there's actually, so Emily mentioned this earlier, there's going to be, we're having a webinar on the 27th that is going to be about multimodal models. And multimodal models will allow you to do vector search between text, images, audio, whatever it is that the model is trained on. So yeah, that's pretty much all I wanted to cover here. I've left quite a bit of time at the end for questions. If there aren't a lot of questions, I can also go over this actual code itself, and we can kind of take a look at how this works. I'm going to step through the notebook and we can take a look at how that works. Okay, doesn't look like there are, oh, okay. Please post a link to the notebook. Okay. Yes, I will go get these. I should have had these pulled up. Let me just show you.
While we let Eugen pull up those links, if you guys can drop your questions into the Q&A panel at the bottom, it just helps us not lose them in the chat window.
Okay, chat window to everyone. So this one is reverse painting search. So I'm not going to go over this one because this one takes like 12 minutes or something like that to get all the embeddings. But this one should be the image search, the text search. Yes, so this one's a text search, and this one will allow you to do all the text data. And yeah, so those are the two models, and they both come with those are two notebooks, and they both come with this URL stuff, and you should just be able to run through the notebooks themselves without having to change anything to get them to work. Gil Amsalem, what are the main advantages of Milvus comparing to Pinecone, Vespa, and other players? Great question. I will let you check out the vector database benchmarking tool to see how Milvus and Zillis compare to other vector databases. I can say, everything I want up here. I can say, oh, Milvus is the greatest thing ever, but you're not going to believe me unless you go and test it out yourself. So I really suggest you just go test it out yourself. I will tell you that the way that I see Milvus having an advantage compared to other vector databases is really that the scale that Milvus works at is ridiculous. Like, I think Vespa might also work at a billion scale, but it's definitely not as fast. And it definitely takes longer to load, and it has a higher cost for query per second. But once again, this is what I see as main advantages of Milvus. Please check out the vector database benchmarking tool and check it out yourself. Okay. Tom Tofig. Can you elaborate on utilizing vector databases for anomaly detections? Yes, actually. So we were actually just talking with a company called Galileo about this. Basically anomaly detection, right, is saying like, oh, this data point looks really, really weird. It looks like an outlier. And the way that vector databases work is like, essentially you're creating all these clusters, right? Remember the IVF image that I showed? It creates all these clusters, or the Annoy one, right? It creates all these clusters of data. Even HNSW does it. It just doesn't, like, the image just didn't show it. So when you query, if your vector that you're querying with is really, really far out there, it's like a really far distance away, then you know that that's an anomaly, and that's probably wrong. Okay. Christoph Bussler, not sure how related it is. When using large text, often it is recommended to be broken up into pieces and embeddings created for each piece. What is the best granularity? Page, paragraph, sentence? This is a use case by use case thing. Unfortunately, I cannot tell you what the best granularity is for every single piece of text. But I will say, sentence transformers is mainly trained to work on sentences. So I would suggest taking a look at that.
I actually have something to add to this. Sorry to jump in, but we have a webinar coming up. It's not on our website yet, but it hopefully will be by the end of next week. So we're doing a webinar August. Let me get the date for you. August 24th with Lance from LangChain, and he's actually going to talk about how to sort of chunk data or chunk text and sort of maintain a lot of the context within sort of those documents. So that's definitely worth checking out if you are interested.
Oh yeah, I actually talked with Lance about this recently as well. So what Lance said to me about what LangChain was doing is they're doing this thing that is called like smart chunking. What I can tell right now, it looks like it's still rule-based. What it is you give it some sort of chunk size and then you give some sort of overlap. So that is part of the thing. Is like, for context, you do want some overlap between your texts to keep the context. But yeah, chunk size, completely up to you. Tom Tofig. Specifically, I'm interested to compare unstructured key performance indicators for wireless networks. That
was the question related. That was an add-on to the question about anomaly detection.
Okay. I mean, yeah, you can put your KPIs into a vector, and then you can see if they're like, you can store all of them, and then like as they come in, you can say, hey, is this one like really far off from the usual? And if it is, then it's probably an anomaly. Mohammed, can you please give the clue to use Zillus for gene prioritization based on similarity? Wow. So this is the first time I've gotten this question. This is cool. You're working on gene similarity. I mean, like, you can get your gene similarity and gene vector embeddings. I don't know anything about genes, to be honest. I know that we've discovered the entire human genome and that it's pretty small. But you can just get your genes, get an embedding for them, and essentially what Zillus can help you do is find the most similar gene that you have already created a vector embedding for, compared to the gene that you would like to search with. Alex, can you suggest the best encoder for PDFs? Why not sentence transformers? Or have I just misunderstood what you said? PDFs are a weird data type. Okay, so PDFs are actually particularly challenging, and this is something that we're working with as well. I'm working on how how can we ingest PDFs into a vector database? Because PDFs actually contain many mixed types of data. So PDFs contain images, they contain graphs, and they contain your text, right? Can you use sentence transformers for a PDF? The answer is yes, but you will have to extract your sentences out of the PDF. So if you just like pass in like, PDF format, it's not going to work. So you have to remember that you have to extract your sentences into some sort of workable format, basically. I don't have an answer for what the best encoder is for PDFs, to be honest. This is a real problem that is being worked on by many people. Tom Tofi, I like to copy those links in chat. Can you please email them to me? Wait, what? Can you copy? I mean, sure, I can, yes. Alex, like with a LangChain loader, for instance. Sure, yeah. You could use a LangChain loader to load PDF documents if that is what you would like to do. Kirill, how big should be the amount of data that we are embedding to have benefit of using Zillus database instead of Face Node and store the embeddings in Firestore, for example? How big should the amount of data? I mean, it's not just about the data size. I would say you probably also want to look at like things like, different ways to index. So Face is an indexing algorithm. That is correct. I don't know what Face Node is. Maybe is that like specifically for Node? I don't know. But Face is a specific indexing algorithm. But as we were saying earlier, vector databases provide many more things to you. For example, if you want to do some filtering on your data, if you have metadata and you want to do some filtering, you're going to want to use something like Zillus. Or, if you want to be able to do tons of transactions, you're probably going to use something like Zillus. So if you're building like a POC, like just for fun kind of app where it's like, oh, I've got 100 embeddings and they're all pretty small, like it's chill. Use whatever you want. Use Face, use HNSW, use whatever. It doesn't matter. But when you get into scale, when you get into really being able to use the vector database for more complex queries, not just comparing your vectors, that's when you're going to want to use like Zillus or Milvus or something like that. Gil, do you use open source engines like Face, Lucene, etc., or do you use a proprietary engine? I'm going to interpret this as asking about these indexes. And we use many publicly available ones as well as ones that we've created ourselves. And you can choose them. So one of the cool things about Milvus is that it allows you to choose your index type, unlike many other vector databases, which will go unnamed. Rock, this is @Tom. You could click on the link and copy it from the URL bar. You can also download it or copy it to your Google Drive. Yeah, exactly. Alex, can you expand on the topic of hybrid search, please, and how Milvus supports it? Yeah, sure. So hybrid search is this ability to so you'll actually see this term used multiple ways. The way that some people use it is it allows you to search like vector types, like BM25. The way that other people use it is it allows you to search this unstructured and structured data, which is actually something that I see a lot of questions about in industry. I've talked to some people who are like, yeah, one of the things we really want to figure out is how can we query like these key value structured data along with vectors as our unstructured data. But the way that I kind of see it is like, look, you have your vector data and you can store your metadata with that, and you can filter over that metadata. And that's what I think of as the real hybrid search, is filtering over like the data that comes with your vector. You can also think about different ways to do that, but that's kind of how I think about it. And what it allows you to do, what it does when it goes in and does a search, and why it's efficient, is that it applies this bit mask onto all of the metadata filter, all the metadata, and it says, if this metadata doesn't follow this bit mask, just skip it, don't do the calculations at all. So that's why it's efficient. Do you support an approximate search of binary data, not vectors, based on Hamming distance? I don't know the answer to this, actually. Emily, do you know the answer to this?
I don't.
Okay, I'm going to say no. Yeah. Sam Corbo, do you guys use GPU for index creation only, or do you use it during the search phase as well? Yeah, so the GPU is used, I think it's used during the search phase as well, because essentially what it is it's NVIDIA's provided GPU support for Milvus that allows Milvus to use a GPU instead of a CPU to do the calculations. So yeah, it has to be using a query phase. Francisco, the metadata capability is meant to bring you closer to standard relational databases. Postgres now has vectors in it to bring the same gap, but in the opposite direction. What is Postgres missing in its implementation versus a vector database? Why would you choose one for the other? So I don't know if metadata capability is really meant to bring you closer to standard relational databases. You can see it that way. I think the metadata capability is really solving this issue of we want to be able to tag our data. We want to be able to see, like, you know, when it happens or where it's from, or maybe like some other like tag is kind of the way I see metadata. I don't think it really gets you that much closer to, it's not like we can't like search like, you know, like I just want the users in this table where, you know, like select from where or whatever. But yes, Postgres does have vectors. PG vector is a thing. And what is Postgres missing in its implementation versus a vector database? Well, it's pretty early on. We have been around since 2017, so we've had a long time to work on Milvus, and we have a pretty active community. In fact, the PyMilvus SDK that you guys saw me use earlier was actually contributed by a community member. But Postgres is, well, one thing, Postgres only has one type of indexing method. So Postgres, right? So we have these multiple indexing methods. I believe Postgres is only IDF. And it's also like, it's not optimized for vector search, right? So what is one of the things about vector search that makes it so different from this like searching relational databases is that you have to do a ton of calculations, right? These vectors are, you know, these long numbers, this long series of numbers, you have to do a lot of calculations on these numbers. And so if you have an implementation that is just basically brute forcing this, or, you know, using, you know, something that isn't optimized for this kind of calculations, you're going to have a slower, you're going to have worse performance, basically. Why would you choose one versus the other? If I'm doing anything with similarity search, I'm going to be using a vector database. I'm going to be using Milvus. If I want to do like, you know, if I have a lot of key value data, such as a user database, I would definitely be using Postgres, or like some sort of org database, whatever. I would definitely be using Postgres, right? But, you know, I really think that as we move into this world of LLMs, as we move into this world of more machine learning focused things, we're really going to be looking at more unstructured data, more unstructured data, more vector embeddings, and really vector databases are going to be really important for that. Vector search is not for finding exact matching, right? So it can find exact matches. In fact, so for example, in this one, I got an exact match right here, right? So what was this? Who is this a painting by? Degas? Yeah. So for example, in this one, I got a match for my Degas painting, and there's actually two of them in there, but you'll see that, you know, you get the distance, and so this distance is basically 0. So you will see these matches. You can get exact matches as well, but it's primarily used for similarity search. Cool. That's all that's in the Q&A. OSS vector. Oh, and that's Emily. Oh. What is this? Vector search with PostgreSQL. Wow, okay, that's a it's a funny picture. Postgres actually has so powerful add-on to manage vectors. Okay, this is not a question, so I don't really know what to tell you there. Okay, we got 5 minutes left. If anybody else has, oh, what happened to my? Can you guys see the screen?
We're seeing your, there we go.
Okay, I don't know what happened to my screen there for a second.
Since it looks like we've wrapped up the rest of the questions, we just wanted to thank everybody for joining us today. Eugen, thank you for such a great session. We covered definitely a lot of material. So everybody keep an eye out. We'll send out a link to the replay. So if there's anything you missed or want to go back and review, you'll definitely have time to do that. Thanks so much, and we'll hope to see you on a future webinar. Thanks, Eugen.
Cool. Thanks, guys.